Our next speaker is Ken Roy. He's going to be talking about transforming Venus and similar planets. He describes himself as a relic of the Manhattan Project and the nuclear age.
I don't think I use that term. But,
well, that's what it said here.
But close enough. Yeah, all right, all right.
Okay, so let's thank him again.
Yeah, I'm going to be talking about an approach to terraforming Venus, but although I'm going to be talking specifically about Venus, just keep in mind that this same approach is probably usable with other terrestrial planets that have really, really thick atmospheres. We don't have another such planet in our solar system, but there may be others in other solar systems. So let's talk about Venus. It's got a mass pretty close to Earth, surface gravity pretty close to Earth, 90%. No plate tectonics. It's got one massive plate, which means it has large shield volcanoes. We think they're active, which means it's got a molten core. It rotates very, very slowly. Its solar day is 117 Earth days. Oh, okay. Here's the material that we expect to find on the surface of Venus, and pretty similar to what we have here on Earth: oxygen, silicon, aluminum, iron, and there seem to be a lot of asteroidal impacts. So we have that material as well if we can get to the surface. The problem with the surface is it's very hot, and the pressure is very high. Temperature 460, 470 degrees C, which is way higher than my oven goes, and 92 atmospheres of pressure. So the pressure is 92 times what we're experiencing here in this room. So it's a high temperature, high pressure environment. We don't know how to function in that environment, which doesn't mean we won't at some point in the future figure out how to do that. But right now it's a challenge. The atmosphere is, very massive, about 93 times what it is here on Earth, as far as mass. Mainly CO2, a little bit of nitrogen. That's relative. The actual nitrogen inventory in the Venusian atmosphere is about 3 or 4 times what it is here on Earth. So they have a lot more nitrogen than we do. And then some, other trace elements. The pressure, and well, let's see, this is a temperature plot with the altitude. So, it starts out very hot, cools off as you go up in the atmosphere. And here around, 50, 60 kilometers, it gets to be, pretty Earth-like. Blue is Earth, green is Venus. And here we see some clouds. There's a lot of sulfuric acid clouds in the atmosphere of Venus, which presents a challenge. And also up in the upper atmosphere, the winds are very, very severe. So there are some challenges with dealing with the atmosphere. Geoffrey Landis has been proposing this idea for some time. I guess there are others that advocate it, but I always hear it from Geoffrey. And his idea is that about 50 kilometers, 55 kilometers, the pressure and temperature is essentially Earth-like. You're still CO2, that's the atmospheric CO2, but that allows you to use oxygen and nitrogen as a lifting gas, and there's no reason you can't use hydrogen or helium as well to get more buoyancy. One advantage of that is you still have a lot of atmosphere above you, which provides a good radiation shield. We have enough atmosphere, to float around the planet, and it's a good area a good location to study the planet and study the atmosphere. And there's no reason we cannot scale that up and actually make the structures bigger, floating cities with reasonably large human populations. And we'll come back to the buoyancy idea here in a little bit. Here's one of the traditional terraforming schemes that has been proposed to terraform Mars. I won't go into great detail. The idea is that you seed it with bacteria and lots of hydrogen, and that converts over time the atmosphere to oxygen, nitrogen, water, CO2, very, very Earth-like. The problem is, again, lots of hydrogen, 4 times 10 to the 16th tons of hydrogen. And we were just talking earlier about how resources are fairly precious, so we need to be careful with that. And also, it's going to take greater than 10,000, up to 1,000,000 years for this process to run to completion. So what I'm proposing is something, I don't know, a way to cheat maybe. I'm not quite sure that's the right term. But we have Venus here, and then we're going to construct a material shell in the atmosphere, some altitude above the surface. And we're going to try to enclose most of the original atmosphere under the shell. We want a Earth normal atmosphere on top of the shell, and this is where we would construct our biosphere, once we have the shell and the atmosphere corrected. This sphere has a surface area of about 3 times the land area of Earth. So, it's terraforming. It's working with a planetary scale areas. Let's talk a little bit about the shell. We're going to have 1 atmosphere pressure on top. We're going to have like 3.1 atmospheres below. That gives you a contained pressure of 2.1 atmosphere. We know how to calculate the resulting tensile stress within the shell, and we use this formula here. Assuming that the shell itself is going to be 1 meter thick steel. In reality, it would be a much more complex alloy, probably a much better engineered design than just a steel plate. And if you work out the numbers here, the tensile stress is humongous, far stronger than any kind of material that we have. But there's another force in play, and that is gravity. Gravity pulls on the shell, inducing compressive stress. And we know how to calculate that. Here you have to include the mass of Venus, because that's what provides the gravity. And if you put it into the equation, we end up again with a humongous compressive stress, not quite as big as the tensile stress, but pretty big. This suggests the possibility of being clever and making these 2 stresses cancel out. And we do that by adding dead weight on top of the shell to increase the compressive stress. In this case, using the example that I just talked about, we need like 11 meters of dry regolith, assuming that the regolith has a density 1,500 kilogram per cubic meter. One question that comes up when you talk about shells is, yeah, hey, that's fine, but is it stable? And it turns out that in this case, yes, it is. As long as the central body is big enough to create a barometric effect that's large enough, it causes the shell to be pushed back in place if it's displaced. Because the pressure as you approach the surface gets bigger, and the pressure as you leave, get further away from the surface, gets smaller. So it's pull and push it. So it's pretty stable. This is an article published in Geodesic that talked about that particular question. So yeah, the shell is stable if we can get it constructed. Before we get too far, we need to talk about a couple of things. Venus is hot. We probably need to cool it off a little bit, at least cool off the atmosphere and maybe dampen down the winds. And also, terraforming is a very energy-intensive operation. The answer, I think, to both is to construct a solar shade at the L1 point between Venus and the Sun. The advantage of the L1 point is that it's always between the planet and the Sun. So if we put this solar shade there and make it big enough, in this case it's going to be slightly bigger than the diameter of the planet, we can plunge Venus into complete darkness. And if we put solar cells on this solar shade, we can collect a lot of energy. And if we beam it to terraforming facilities on and around Venus and assume a 10% efficiency, we have 30 terawatts to work with. And you'll have 30 terawatts as long as you want. So I've been talking about 43 kilometers above the surface. It doesn't have to be 43. You can build it different altitudes. this column is altitude, this column is temperature. Depending on the altitude you choose, that's the temperature you get. Here's the pressure you get. Again, it's determined by altitude. Again, I'm assuming the initial shell is like 1 meter thick steel plate. And in order to get the final stresses to equal out, you have to make sure that the final mass loading is in this column here. So at 43 kilometers, we're looking at, what is that, about 24 tons per square meter. So, not a tiny shell, it's going to be a fairly massive structure. The shell itself, I'm thinking, will be based on a geodesic sphere design. The shell components would essentially be hexagons. I'm assuming here, for no particular reason, that the side width is about 20 kilometers. That gives you an area of about 1,000 square kilometers. Mass is pretty big. Also, I'm including an atmospheric processor on each element. We'll talk about that a little bit longer. And in order to, complete the shell, you're going to need about 450,000 of these elements. So terraforming is not for the faint-hearted. The Venusian shell, these elements, we want to position them at the 43 kilometer altitude, but there's no shell, so how are we going to support them? And here we get back to buoyancy. Hydrogen and helium are, very, very effective lift gases. Again, if we assume, 8 metric tons per square meter, if the balloon is 2 kilometers high and the same area as the shell, then we can float this thing around the altitude that we need it. The shell components, you can either manufacture them in orbit or you can manufacture them on the surface. If you manufacture it in orbit, you're going to need an asteroid. If you have a nickel-iron asteroid, about 96 kilometers in diameter, you have the mass that you need to construct the shell. If you build it on the surface, you can use surface materials. The only thing you're going to be short of is hydrogen, which you'll have to import. So how do we put it all together? Once we have the shell components floating around at the altitude that they need to be, then they will self-assemble or be assembled into a complete shell, something like this. I mentioned the atmospheric processors on each element. Those are essentially big compressors, big fans, and they're powerful enough you should be able to use them for altitude, attitude, and even thrust for the individual shell component. So it can maneuver where it needs to be. Okay, once we have the shell in place, we turn on the atmospheric processors, and they begin sucking the atmosphere above the shell and discharging it below the shell. The goal is to go from 3.1 atmospheres to 1 atmosphere. And as you do that, the tension in the shell begins to increase, and you first counter that by deflating the balloons. And once the balloons are completely deflated, you have to add mass to the shell in order to achieve the 24 metric tons per square meter in order to keep the stresses equal. So what do we do? Well, okay, this is a little bit of detail. We're going to have to pump 70% of the atmosphere originally above the shell below it. That's 1.1 10 to the 16th tons of atmosphere that's going to have to be removed. If you crank through the numbers, if you want it done in 100 years, then each processor is going to have to be, throwing 480 tons per minute. If you're willing to take 150 years, 300 tons per minute. So, yeah, these things are not minor. But then we know how to build fans and compressors. Okay, once we have 1 atmosphere of pressure above the shell, keep in mind it's still the Venusian atmosphere, and that is mainly CO2. So what we want to do is convert this CO2 into oxygen and carbon. And so the atmospheric processors would, break up the CO2, discharge the oxygen above. The carbon we can either use to make structural elements, add to the soil that we're going to need to, convert to a living soil, or just dump it on the surface of Venus. And also, we're going to need to remove all the SO2 and sulfuric acid that's above. So that's going to be a challenge. But where does the nitrogen come from? Again, we're going to have to use atmospheric processors to take a stream of the Venetian atmosphere and strip out the nitrogen and inject it above the shell. Nitrogen and argon. It has plenty of nitrogen, but it's a little short on argon. We won't be able to duplicate Earth's argon supply, but that's okay. The final shell configuration, could look like a lot of different things. This is one harebrained scheme. This is the structural shell here, the 1 meter thick steel. This is insulation. Aerogel looks pretty promising as a potential insulation. The temperature here is around 100 C, so we do want to slow up heat transfer into the shell. This is atmospheric processors, but also we've added utilities, electrical distribution, water distribution, communications, maybe factories, warehouses. This is kind of the industrial area. And there are also columns and beams that support what I call the ground level. This is a steel base, and then on top of that you've got rock and minerals that you're going to convert into the living soil. And that's a complex problem that I'm not going to get into. But you have 1 atmosphere of pressure above it, which is oxygen, nitrogen, and this is where the biosphere is going to be constructed. We can also use oceans, install oceans if you're willing to limit your water to no more than 16 meters. We can have oceans, lakes, whatever you want. And again, I'm assuming we have insulation here. The water is directly on the structural shell, so you're going to have to deal with corrosion issues, understanding that big leaks lead to problems. And you're also going to have to come up with lots of hydrogen or maybe a few big comets. This is going to be, a 1,000-year project, so if it takes a while to get the comet in orbit, well, we could probably live with that. But one advantage of this is it simplifies the mass loading question quite a bit. Okay, final steps. Keep in mind the shell is not in any way connected to the planet below, so we can spin it up using our atmospheric processors, that slowly begin to accelerate the shell. And we can achieve a 24-hour day-night cycle, or any cycle we choose. We adjust the solar shade to achieve the kind of climate and temperature profile that we desire. We need to get the hydraulic cycle going. We need to convert the minerals, the clay, the silicates, the carbon that we put on top of the ground level, convert that into living soil. And that's a complex question. We need to introduce Earth life, and we can even build an artificial moon that simulates Earth's moon as far as period, size, and brightness. So it can be a very, very Earth-like setting. So move in. You have a surface area that's 3 times the land area of Earth. Now keep in mind it's a structure, so it's going to require maintenance and repair, which might lead to an interesting society because their lives literally depend on it. In the terraforming discussion last night, someone pointed out to me that humanity is probably selfish enough not to engage in a 1,000-year or 1,500-year enterprise if the payoff doesn't have some intermediate returns. And I thought about that, and one of the papers I came across when I was putting this together speculated that there was a lot of helium-3 in the Venetian atmosphere. 2 times 10 to the 10th tons of helium-3 in the Venetian atmosphere. And again, remember our atmospheric processors. We're stripping nitrogen and argon out. If we can also strip out helium, we can provide a lot of helium-3 for a long time, if the estimate of the helium-3 inventory on Mars is in place. So, any questions or comments?
I'm almost ready to move in, but I'd love lakes or oceans there. Have any thought about calculations, how it changes at all if you wanted some, lakes for recreation or just to make it?
If you're going to have a living planet, you actually need oceans. So you will have to have oceans there, and that's kind of a designer choice. How big, how much, but you can't go over 16 meters deep. That's a hard limit.
Yeah. So you were talking about helium-3. Any idea how does I don't know how that number compares to the amount of helium-3 in the Earth's atmosphere.
Venus is actually, again, this paper assumed that Venus was a much better trap of helium-3 from the sun than the moon was. It has no magnetic field to speak of, so all that solar wind containing a lot of helium-3, hits Venus, gets stuck in the atmosphere, and circulates. So the ratio of helium-3, it is speculated, is far higher than it is here in Earth's atmosphere.
Given that it escapes from the Earth's atmosphere, which is the problem, why would it not escape from have escaped from Venus's atmosphere, which is warmer?
Oh, it does. It does. But again, once it's in the Venusian atmosphere, it takes a lot of work for it to, get to the top and escape. The helium-3 on the moon also escapes due to heat, and the low gravity. So, it's an interesting paper, and it's an interesting prospect. I would dig into that more.
So you had mentioned that obviously maintaining the shell is important, yes?
Yes.
How susceptible, or what does it look like if the shell has like small structural deformities? Could you design this in a way that it doesn't implode and destroy the entire shell?
Oh yeah. You want to make it as durable as you can, and if you have 1 meter thick steel, it'll take some variation in mass loadings. It'll distribute it out. If there's some deformity, small leaks are not the end of the world, because there will be repair machines that are continually walking around looking for problems and will repair it. That's one reason I had that tween space, so that the repair robots can look at the top of the shell, and then the insulation I had hung below it. So again, robots can walk around and inspect the shell, because that's life and death to keep that thing healthy.
Yeah, so over here. Is there a reason why only having half the amount of Earth-based argon would be particularly detrimental? I mean, argon being an inert gas, it's not exactly used within metabolic processes, but it is industrial important. Is that where you were trying to go with that point? I'm not.
No, when the definition of terraforming is forming an Earth-like planet. And so what I was trying to do was, to the extent possible, duplicate the atmosphere here on Earth, which is about 1% argon. And if we just use resources from Venus, we can't get there. But then on the other hand, argon is pretty worthless from a biological standpoint. Correct me if I'm wrong. So I think we could leave it out and just replace it with nitrogen without any big problems. Geoffrey, he has a criticism. Yes, I know.
No, actually, I like it. You remind me of Paul Birch. This is exactly the sort of thing that Paul Birch would love to propose. I'm just pointing out that it would probably be worth putting multiple shells around the planet instead of just one. There's plenty of atmospheric pressure to support more than a single shell. And if you put 2 shells over it, gives you a lot of redundancy against single point failure.
That's certainly a possibility. That just takes more steel and more time. And
well, actually, each shell could be half the thickness. It wouldn't even take more.
That's right.
More
That's
steel. Right. But it would give you the redundancy against single point failure. I noticed that your atmospheric processing plants are still going to be there. So a certain amount of leaking is not really a big problem. You just use the same atmospheric processing plants that you'd use to start with.
Right. And again, that's one reason I put that tween space in there, because leaks will come up there, and that's where the processor will deal with it.
In fact, you could put an arbitrary number of shells of
that's true.
Infinitesimal thickness if you wanted to, but probably at least 2 would be valuable.
Right.
So as you're increasingly making your terraforming more complex, and you're adding steel and then soil on top of that, and you're increasing your industrial, how are you going to then offset the compressive force by adding more structure to the outside with the constant tensile force just from the planet itself? Are you going to have to then launch some of this structure that you had put in place in order to counteract the tension and compression in order to account for that increased structure?
I would anticipate that there's active monitoring of the stress within the shell, at all times. And if it starts to get out of parameters, say if there's too much compression, then you actually have to move mass in to begin to counter that particular stress. If the tension gets too big, then you can actually dump or move mass out of the way. So, yeah, the care and feeding of this thing is something I didn't have time to go into. But yeah, you're going to have to monitor in real time the stress that is occurring, and you're going to have to shift mass around. And you can actually dump, mass on the surface of the planet if you need to. So.
Okay, let's thank our speaker again.